Good morning. Welcome to the video on power quality. In this video, we are going to discuss about the two-wire passive compensator. And let us discuss about the nomenclature over here. The supply voltage is the Vs and Is is the supply current. The transmission line is having a resistance and the transmission line inductance is represented by Rs and Ls. The load is represented, usually we represent the load by R plus JXL, where R is the load resistance and XL is the load inductance. Usually the loads are inductive in nature. So what we will doing here, we are representing this ZL as a YL. Instead of having an impedance, we are getting the admittance. So if we are writing in terms of admittance, we know that Y is equal to 1 by ZL. And if we write this 1 by ZL, rewrite this 1 by ZL, what will be? So I can write this 1 by ZL is equal to 1 by RL plus JXL. And if I multiply both sides with R minus JXL and bottom also R minus JXL, so what I'm going to get is, on the top we will getting the R minus JXL. At the bottom we will be getting the R square plus XL square. So obviously these two will be taken out one side and it will be said as G, and the term with X will be termed as B. So we are going to get a term, this R by root of a square, not square root, R by R square plus JXL is equal to R by R square plus XL square is equal to GL, and minus of J or XL by R square plus XL square will be BL. So here we are writing in terms of GL conductance and BL susceptance, conductance minus of J BL in this way. So the easier part of it is that whatever the susceptance part of it, we just need to go and do the compensation for that and get the value of J BC. So these two, in easy language, we can see that these two cancel each other, or we can cancel each other, so we get in terms of resistive only. So the power factor need to be improved here, that VL is here, you have a supply current is here. If these two are in phase, then the power factor at the load end is improved. So how to do that? So we will try to we will try to draw the phasor diagram. So to draw the phasor diagram here, so we will take the reference as a VL, both in the same screen. So if VL is the reference over here, so VL is taken as reference in the x-axis. So whatever we are doing to do, we do with the VL only. So if the VL is here, so I will multiply this VL with GL, which doesn't have any J term. So this will be VL into JL, which doesn't have any J term, will be along the x-axis. Another will be VL into BL, which is having a minus of J term. So obviously this will be negative y-axis, minus of J VL into BL. Similarly, we have got a VL multiplied with the JBC, which is having a positive J, which is positive y-axis. So here we have JVL into BC, and what it decides the IC. IC is the current in the upward direction. So now if we multiply this VL with the admittance, what we get is the IL value. So if we these two phasors, if we add, we get the direction of the IL here, and this IL is IL and the IC. IL and this IL and IC leads to the value of IS. So now the value of IC we have in our hand to adjust by changing the value of JBC or BC value. So that will give us, IL and IC can give us the direction of IS over here. Now that gives the power factor correction at the load terminal with VL and IS in phase. Now this IS, if we multiply with the RS, and this IS when we multiply with the J axis, we are getting this line. That means we are adding this VL, the potential over these 2 points. Then we add this IS into RS. Then we add this IS into JXL. So we add this potential, and this potential. 3 potential we add. That is VL, then IS into RS, then this potential. If we add these 3, we get the value of VS. And this is how the phasor diagram of the power factor correction at load end is formed. Thank you. In another video, we will see for another phasor diagram for this particular picture.